Hello, in this video we're going to go over this problem. Evaluate the integral from 0 to 1 of x to the fourth times 1 minus x to the fourth divided by 1 plus x squared. Okay, so here is how I approach this problem. There are several things that I tried and one of them worked better than the others. The first one was I wanted to use the limit swapping technique for integrals, which is a way we can evaluate the definite integrals without actually doing the indefinite integral. So in this instance, a way to swap the two limits of integration is to do a u substitution of 1 minus x. If we do that, we get du equals negative dx, and the integral becomes integral 1 minus u to the power of 4 u to the power of 4 over 1 plus 1 minus to u to the power of 4 negative du, and if x is 0 we get u equals 1, and if x is 1 you get u equals 0. Taking the negative sign and swapping the limits of integration, we get u to the fourth 1 minus u to the fourth over 1 plus 1 minus u to the fourth du. Okay, so now oftentimes what happens is that when we add these two, so if I call this integral I, twice I would be the sum of these two integrals, integral from 0 to 1 of x to the fourth 1 minus x to the fourth over 1 plus x squared, and x to the fourth 1 minus x to the fourth over 1 plus 1 minus x to the squared, and this would actually have to be squared here, dx. This didn't really make things simpler because of the fact that the denominator is actually quite complicated. So we get 1 plus 1 minus x squared, and then we'll have to factor x to the fourth times 1 minus x to the fourth times 1 plus 1 minus x squared plus 1 plus x squared. Simplifying that, it actually didn't make things any simpler, but if you are able to solve this one, do let me know. So at this point I just basically stopped this idea. So let me go back and rewrite the given integral. So when I thought when I got to this one was basically, let's multiply the x to the fourth and 1 minus x to the fourth. We get x minus x squared to the fourth over 1 plus x squared dx. Okay, so this is a rational function. The usual way of evaluating integrals of rational function is to use partial fractions. In this case, the denominator is a quadratic without any roots, so we don't really need to use partial fractions, but we have to use the first step of the partial fraction, which is to divide the numerator by the denominator. Now, you can expand this whole thing and then divide the numerator by the denominator. It does get a bit messy, but there's a better way of dividing, which is what I did. I said, okay, so I'm going to create x squared plus 1 on top. So I will write this one as x plus 1 minus 1 plus x squared to the fourth over 1 plus x squared dx. If you expand the numerator using binomial formula, we get x plus 1 to the fourth minus 4 x plus 1 cubed 1 plus x squared plus 6 1 plus x, or x plus 1 doesn't really matter, squared 1 plus x squared squared minus 4 x plus 1 cubed. Okay, maybe I'll write this down here. Minus 4 x plus 1 plus x squared cubed, and then finally plus 1 plus x squared to the fourth over 1 plus x squared dx. Now we can simplify this quite a bit. So the first term can't really be simplified. We get x plus 1 to the fourth over 1 plus x squared. The rest of the terms all have x squared plus 1, so we can get rid of 1 plus x squared in the second term. This guy and this guy cancel. The next term is going to be plus 6 times x plus 1 squared and then there's going to be a 1 plus x squared because it's 1 plus x squared squared, and then the next term is minus 4 x plus 1 plus x squared squared, and then finally we get 1 plus x squared cubed dx. Okay, so this is something that I can definitely solve. It does get quite a bit of a mess, so this can be just expanded. It's a polynomial and you can integrate. Certainly that's possible. And for this one, we will have to again divide the numerator by the denominator. So you'll have to expand the numerator, divide it by the denominator, and then you're either going to get natural log or you're going to get tangent inverse of x, and then you'll go from there. So it's definitely possible to solve. And if I really had to solve this problem and I had time, then I would just go that route. However, at this point, I realized that, okay, maybe there's a better way of doing this one. I didn't want to spend, half an hour just expanding these and dividing and taking the integral. So, is there a better way of doing this one? And for that, let me rewrite the integral. So that's x minus x squared to the power of 4th over 1 plus x squared dx. So seeing 1 plus x squared at the bottom, a natural substitution would be x equals tangent of u. Now, if I do that, then I would get dx equals secant squared of u du. When x is 0, and of course when you do that substitution, u would be between negative pi over 2 and pi over 2. When x is 0, tangent of u is 0, so u would be 0. When x is 1, tangent of u is 1, so u would be pi over 4 in that range. We get tan u minus tan squared u to the power of 4 divided by 1 plus tan squared of u times secant squared of u and then du. So that's equal to integral from 0 to pi over 4. Okay, so now if I look at this one, secant squared of u and 1 plus tan squared of u are in fact the exact same thing. So we can cancel those two. And we are left with tan of u minus tan squared of u to the power of 4 du. So now I'm going to just expand this to see what we get. We get tan to the 4th of u minus 4 tan cubed times tan squared, tan to the 5th, plus 6 tan squared times tan squared squared, that's tan to the 6th, minus 4 tan to the 7th, because you get tan times tan squared to the power of 3, and then plus tan to the 8th of u du. Okay, so this is what we get. Now notice that tan of u, the derivative of tan of u, is 1 plus tan squared. So I can take this guy and this guy and factor negative 4 tan to the power of 5th, and I'm left with 1 plus tan squared. So this is nice because derivative of tangent is 1 plus tan squared. This is derivative of tangent. And then this is not very difficult to integrate. I can do the same thing with this guy and this guy. So if you factor from those two, if you factor tan to the power of 4, you are left with 1 plus tan squared. Now, if you do that with 5 of those, and then keep the last one for this guy and this guy, for these two, we get tan to the power of 6 of x, or in fact u in this case, we had u. Let me just keep u here. times 1 plus tan squared of u. Now, I have to subtract 4 tan to the power of 4 of u. So this completely balances out everything. This is derivative of tangent. This is also derivative of tangent. So I can pretty easily integrate the first 3 terms. This term, and this term. So let's check these again. So we have negative 4 tan to the power of 5th, negative 4 tan to the power of 7. So it checks out this guy and this guy. This one gives you plus 5 tan to the power of 4 minus 4 tan to the power of 4. So that's tan to the power of 4. So it checks out this one. This one gives you 5 tan to the power of 6. This one gives you tan to the power of 6. So that checks out this one. And this one is tan to the power of 8. So we are good with all of that. Now, this is integral from 0 to pi over 4. Negative 4 tan to the power of 5th plus 5 tan to the power of 4th plus tan to the power of 6 times 1 plus tan squared, which again is the derivative of 1 plus tan squared, minus 4. We can also factor this guy as tan squared of u minus 1 times tan squared of u plus 1. But if we do that, then we're left with minus 4. Because this would give you tan to the power of 4th minus 1. And then you have to subtract 4 to balance things out. So we get this equality. Now again, this is also derivative of tangent. So we get negative. So we're going to just integrate. Derivative of the integral of this one, this is basically d tangent, would be minus 4 tan to the power of 6 over 6 plus tan to the power of 5th plus tan to the power of 7 over 7 minus 4 tan cubed over 3 and then minus tan of u. All of that goes from 0 to pi over 4 and then minus 4u. Again 0 to pi over 4. Okay, so we're really almost there. Plug in pi over 4 here, we get negative 2/3 plus 1 over 7 minus 4 1/3 minus 1. Plug in 0, we get all 0 and then minus pi. Okay, so this is pretty easy now to calculate. So this is 1/3 plus 1 over 7 minus, this is negative 2/3, so that's 8 over 3 plus 8 over 3 minus pi. So this gives us 3, 1/3 and 8/3 is 3. So that's 22 over 7 minus pi. So that is the final answer to the problem.